Hey everyone, welcome back. Math 7195, Unit 2, Video 2 on probability. Today we're going to be discussing at least situations, conditional probabilities, and Bayes' theorem. So we can just go ahead and dive right in here. At least situations are problems where it turns out to be much simpler to work with the complement than to work with solving the problem directly. An example of this might be, what's the probability of at least one success? If we were solving that directly, we would first find the probability of one success, then find the probability of two successes, then find the probability of three successes, etc., and so on. And then we would sum all these together, assuming they were mutually exclusive. If they weren't mutually exclusive, it would be even more complicated because we would have to subtract out the parts that overlapped. Rather than do that much work, the simplification is to just do the complement, or the opposite of this. So the opposite of at least one success would be no successes. And we could just solve that one case and then do 100% minus that case, and that would give us our answer. An example of this might be, what's the probability of getting at least one ace if we draw 5 cards? So let's define a variable here. Let x equal number of aces in 5 cards drawn. We want the probability of getting at least one, so one or more. Like I said, to solve this, we could find the probability of exactly 1 plus the probability of exactly 2 plus the probability of exactly 3 aces plus the probability of exactly 4 aces, and there better not be 5 aces, so we can stop there. So we could find these 4 probabilities and then sum them all together. Alternatively, we could just look at the opposite of this problem, which is 1 minus the probability that x is less than 1. The opposite of greater than or equal to will be less than. Because this is a discrete probability, the only value that is less than 1 is none. Now to calculate this, we need to draw 5 cards and have all 5 not be aces. So we need the first card not to be an ace. So we ask, how many non-aces are there? Well, there are 48 out of the 52 cards. And after we've picked our first card that wasn't an ace, now the next card depends on that. These are dependent. The next card has to also not be an ace. But there are only 47 non-aces left and 51 cards left in the deck. Continuing on with that pattern, it'll be 46 out of 50, 45 out of 49, and then 44 out of 48. And we can multiply that out. Now, this is another one of those situations where I have a hard time imagining what this answer is going to be. Is it going to be 70%, 20%, 52%? It's a number sense with probability is a difficult thing. It turns out that this is around 34%, 0.3412. If you're a person that, just really likes to do a lot of work, then I guess we could have solved, that original problem there. It would be quite a bit of work, and it would involve our combinations notation. What's the probability of getting exactly one ace in 5 cards? that's tricky because there's more than one way it can happen. That one ace could be the first card, or it could be the third card. So we would have to, really consider all those possibilities. The probability of exactly no aces is nice because there's only one way that we can rearrange it. It's just they're all non-aces. But when you have one ace, then you have to consider when you get the ace. One way you could do this is to maybe use combinations. You have 4 aces, you need one of them, and the order doesn't matter. And then there are 48 non-aces, and you'd need to pick 4 of those. And then you would divide that by all the different ways that you could choose 5 cards in a deck. This is the probability of just the first piece. Then we'd have to calculate, okay, I have 4 aces in total, but I want to make sure I get 2 of them exactly. And then I have 48 non-aces, and I need to pick 3 of those. Again, it's 52, choose 5 on the bottom. And do this for all 4. I guess it's not too bad if you're comfortable with, this combination notation that we were using. I think we used this when we were doing a question about poker as well. We were doing number of full flushes or something. So this next one is I need 3 aces and 2 non-aces. And then the last term there would be 4 choosing 4. I have 4 aces. I need to get all 4 of them. And then there are 48 other cards. I need to pick one of those. So after doing all these combination calculations, we would arrive at this. So I think we're going to find that this complement idea of trying to find the opposite of something will definitely help us with the more complicated problems. Another example of this is the classic birthday problem. Our class, in a lab, we say we have 25 students. What are the chances that 2 of those students have the same birthday? Usually I poll the class, and students will generally say, oh, well, if there are 25 people, that's 25 out of the 365 days in the year. So they guess that it's around, under 10%. But it turns out that this one is rather shocking. It ends up being much higher. Let's try to calculate it. So let's try to find the probability that we get at least one match in the class. So at least 2 people have the same birthday. At least 2 people match. Now that would be really hard to try to do directly. You have student number 1. They might match student number 2 or 3 or 4 or 5 or 6. But student number 2 might match student number 1 or number 3 or number 5, etc. So you'd have to find all those different permutations, which would be really tricky with such a large number of people. But attacking this problem with the complement is much easier because the opposite of at least one match is no matches. Meaning everyone in the class has a unique birthday from anyone else in the class. We'll make the assumption here that, let's ignore leap year, and let's obviously not care about year, let's just care about birthday. To solve this, I just need to have 25 people with a different birthday. So person number 1, they can have any birthday. There are 365 in total. They may have, well, any of the 365. Then person 2 can't match what person 1 had. So they only have 364 birthdays that they could have out of the 365. And then person number 3 can't match the first 2 people, so that's 363 out of 365. And we just keep going until we get to the 25th person there, who I guess that'd be 340. Geez. We subtract 25 from 365, we get 340. But I think it's going to be 341 out of 365. That'll be the 25th person. Whenever you're having trouble with a sequence like that, imagine the problem being smaller. If I had only 3 people, like I have listed here, you can see the last person, the third person, is not 365 minus 3, it's 365 minus 3 minus 1. So I think that's what the pattern continues here. It'll be 341, not 340. Some of us would recognize that this is, looks like factorial notation. Whoa. Sorry about that. The factorial notation on the top, it looks like 365 factorial, but it stops at 341. So I'd have to divide by 340 factorial. And then divide the whole thing. Each term has 365 in it, so that's 365 raised to the 25th power. Sadly, these numbers are all way too big. Your calculator won't handle 365 factorial. It probably won't handle 365 to the 25. Even Excel can't handle these numbers. We'd have to use, stronger math software to handle these things. I think 70 factorial is over 10 to the 100, and most calculators fail around 10 to the 99. So to calculate this thing, we'd actually have to put these in one by one. 1 minus 365 over 365 times 364 over 364 times, and just grind it all out. It turns out to be shockingly high. It's over 50%. It's 56.87%. In a room with 25 people, there's a better than 50% chance that 2 people will match. Even though there's a very low chance that any 2 people match, it turns out that because there are so many different permutations, all very low chances, but when you add them all together, eventually you start to get a fairly high probability. So this is another one of those cases where your intuition may not be that great when you're solving some of these probability questions. Sadly, it takes a lot of experience before you start to be able to predict probability very well. Last time we were talking about the or situation and the and situation for compound events. We came up with this formula. The probability of A happening and B happening is the probability of A happening times the probability that B happens, given that A already happened. It's sort of what's the probability of A and then B? Well, that formula can be rearranged. Like we can solve this thing for the probability of B given A. Just divide by both sides by the probability of A. And we've just, created a new formula from one that we already had. This is known as sort of a Bayesian probability, where this famous mathematician, if you have information adjust your probability based off of that information. So if you already know that something about the situation, like A already happened, well, adjust the probability of your result based off of that. Here's a little example involving titanium rods. We have this little table. We studied 2,000 titanium rods, and they had various problems and reasons for those problems. Some of them were too long or too short. Some of them, their diameter was wrong. Others had a crack. And some reasons for these things might have been the material was faulty. There was temperature wasn't right in the casting process. Maybe when they were grinding them during the process, that caused some sort of, inconsistency there. So if we look at this chart of the 2000, 12 times we saw a height problem where there was faulty material. 57 times we saw there was a crack and a grinding flaw at the same time. So now we can ask some probability questions about this group of titanium rods. So we have this, say there's a big pile of these things, there's 2,000 of them, and we randomly pick one of those 2,000. What is the probability that the flaw was the result of faulty material if we see that there's a crack in the rod? So we're not just picking one up and saying, what's the probability of a flaw? We're picking one up and saying, we picked it up and we saw a crack. Now, was the material faulty? So what's the probability of faulty material given that we see a crack? Basically, we're applying the formula that's up above. So our A is a crack and our B is faulty material. So substituting these, values into our formula, it's the probability of being cracked and faulty material divided by the probability of getting one that has a crack. So let's see if we can figure this out. We want to find the intersection of cracked and faulty. So that's here. We have faulty material and we have cracks. So their intersection. That notation of using set notation for and works really nicely here. We're saying these two groups intersect here. So there's a 727 out of 2,000 chance of getting one that's cracked and faulty at the same time. And then we'll divide that by the probability of being cracked. To find that, we'll see our total number of cracked is 1426 out of 2,000. That simplifies to just 727 out of 1426. So not too bad. I think you could probably reason these out without the formula. In fact, I tend to not use this formula. Sometimes this formula is maybe even more confusing to me. If I just look at this table and say, okay, I want faulty material given that it's cracked. So the first thing I'm told here is I know that it's cracked. So that reduces me down to this group. I'm in the group of cracked values. What are the chances that it's faulty? Well, there are 727 that are faulty in the cracked category. So I'm just going to look at the ratio there. It's 727 out of 1426. Basically, the given part tells me where the total is. It's kind of nice. This notation is even sort of nice that given symbol looks a lot like divide, and that's what we did. We divided by the total number that were cracked. So it's the number that were faulty within the cracked group divided by the total that were cracked. Let's do another one here just to show that this thing may not be, commutative as expected. What's the probability that one is cracked if I already know that it was a faulty material? So maybe I pick one up and I haven't really inspected it yet, but I can tell that it's faulty material. There's a label on it, or it has a funny color, or some easy way to tell that it was faulty material. Now, I haven't really looked at the thing to notice if there were cracks yet. So what are the chances that after I do search and inspect it, that it will be cracked? Well, we could use the formula, or we could just sort of reason this out. Again, we know that there's faulty material, which means I know I'm in this row. So my total number will be 1118. And I want to know how many of those are cracked. Well, that's the 727. This sort of probability problem is used a lot. The classic example is with testing. We can test, this is the sort of problem that you run into with tests for diseases, for example. We can ask, if you tested positive, what's the probability you actually have the disease? If you tested negative, what's the probability that you actually have the disease? If you have the disease, what's the probability that you will actually test positive for the disease? So those are the classic examples. I tried to turn it into an engineering problem, with cracks and titanium rods, but it's the same process. So if you're ever Googling conditional probability, that's another great example. I mentioned this guy, Thomas Bayes. He was very controversial back in the 1700s. The classic probability theorist didn't like adjusting probability based on given information. So this guy really was sort of on the fringes, but now it's become very accepted. But as far as math goes, he's still relatively recent. 300-year-old math. That's somewhat new compared to a lot of things. Some notation that Bayes came up with was he looked at a bunch of sets and he defined sets were exhaustive if they in some way covered all the possibilities. An example here would be rolling a die. I could define one event to be getting a 1 or a 2, another event to be 3 or a 4, another event to rolling a 5 or a 6, another event might be rolling a 5. Well, these events are exhaustive because as long as I use all 4 of them, I'm guaranteed to have covered all the possibilities, even though there's some, overlap there. So these sets aren't mutually exclusive because set A3 and set A4 have something in common. But the first 3 sets are mutually exclusive. There is no overlap. So if I just consider set A1, A2, and A3, that would be a mutually exclusive and exhaustive set that would, cover all the possibilities for rolling a single die. I want to consider those 3 events that we have above as defined A1 was a 1 or a 2, A2 was a 2 or a 3 or a 4, and A3 was a 5 or a 6. So those are my 3 events. They are exhaustive and they are mutually exclusive. I drew a little kind of crude picture here where I have my 3 groups. A1 was, a 1 or a 2, and A2 was a 3 or a 4, and A3 was a 5 or a 6. I'm interested in a new set called an even roll. Now there are evens in each of these. So that's why I drew a set here. Set B is the probability of getting an even. So I was just trying to visualize this where, okay, so the number 1 would be, say, here. The number 2 would be in there. The number 3 would be here, 4 here, 5 here, 6 here. I'm trying to come up with a formula for finding the probability of an even roll given this situation. Well, basically to get the B, I want to add this piece to this piece to this piece. If I sum those 3 pieces together, then I get B. So these pieces are the intersections. I have A1 and it's even. This section is it's in A2 and it's even. And this section here is it's in A3 and it's even. So I just listed that out. The probability of B is the sum of those 3 pieces. Now we can always take our AND formula and rewrite that using our conditional formula. The probability of A1 and B is the probability of picking A1 and then getting B given that you're in A1. This is just the usual formula for AND. So we're basically just, we're taking something simple like, let's find the probability of B and turning it into this rather large formula. But these pieces are all things that we can solve. So this becomes something known as the rule of total probability. We could do this one, the probability of even is the probability of being in the 1 or 2 set. Now there are 3 sets there and they're all equally likely. So there's a 1/3 chance that I would pick or get a roll of 1 or 2. And then the probability of being even given that is what's the probability of getting this 2 given that you're in this set. So it's a 1/2. And they'll all be that way for this one. You have a 1/3 chance of being in the second block, and there is the number 4 in that group. That's the only even out of 3 and 4. So we can just calculate that out. And hopefully it ends up being what we'd expect it to be. 1/3 times a half, 1/3 times a half, 1/3 times a half ends up being 3/6, which is a half, which is the probability of rolling an even on a single die. Like, we just took one of the simplest problems ever and made it rather complicated, to demonstrate this. But this can be applied to other things as well. It gets generalized. We don't have to just have 3 sets. We could have any number of sets as long as they meet the conditions of being mutually exclusive and exhaustive. The rule of total probability here, I just rewrote it with, more generally, where I have a total of k possible sets. In my example then, I was a little lazy and I only did 3 sets, but here's an example where you have 3 companies, Intel, AMD, and other guys, and they make computer processors. Intel has 85% of the market share, AMD has 10% of the market share, and other people have 5%. If you notice, these market shares add up to 100%. So they are exhaustive. If you get a computer processor, it's from one of these three. It's nice to always put a group called other in there, to cover everything. We have some data from these companies. Intel's been monitoring their chips for a while, and they realize that 1% of theirs are defective. AMD keeps track of theirs. 3% of theirs have problems. And other people keep track of theirs as well, and their problems are around 2%. We have met the conditions for a Bayes question or rule of total probability here because we are exhaustive. You must be from one of these three companies, and they're mutually exclusive. So, a chip isn't made by both Intel and AMD at the same time. Let's not have partnerships. So to try to get the symbols to line up here, I wrote them out. We want the probability of getting a defective chip. If we just reached into a bin of random computer chips and pulled one out, what are the chances that it is defective? Just looking at those percentages, you probably guess it's around 2%. But let's see. My sets are the various companies. The probability of the companies are their market shares. And then their probability of being defective, given we know what company they're in, were also given in the table. To find the total probability of being defective, we simply take those products. What's the probability of it being Intel times the probability that it is defective from Intel? So 85% times 1%. And we just continue on. 10% times 3%, and 5% times 2%. And we add them all together, and we got 1.3%. The reason that it wasn't, we estimated that it was going to be around 2% when we just eyeballed it. The reason it's actually lower is that we don't just take the mean of these three numbers because they're weighted. Basically, we just found the weighted average of these defectives. 85% of the time, we only have 1% defective. So that's the biggest, contributor, and that's why we ended up with a value that was lower than 2%. This, I said it again, we made this pretty complicated. You've probably been using this rule of total probability ever since you became a student, because this is how you calculate your grade in a course. Instead of having Intel, AMD, and other guys, you have a midterm, you have a final exam, and you have other marks, and they have various weights, and then you have your marks in those various components. And that's how you calculate your grade. You just multiply the weight times your grade and add them all up. So as scary as maybe this formula may have made this look, it's fairly intuitive so far. I drew out a little tree diagram, showing the situation. And you can just follow the branches to find the probabilities. You could choose Intel, and then it could be defective. So to get to this part on the branch, I just multiply. It was Intel, and it was defective. To get to this part of the branch, it was Intel, and it was not defective. And we can do that for all of these. When we add them all up, we better get 100%, because this is all the possible things that can happen. What will be interesting, perhaps, is to go the other way. In the problem we just did, it was relatively boring. We reached into a bin of computer chips and we asked what's the probability of it being defective. But what if we wanted to go the other way and say, okay, I know my computer just broke, so I have a defective chip. Who's to blame for it? And I don't want to open my computer up to find out whose fault it is. What are the chances that when I eventually do that, that I would say I could blame Intel? So that will be our question of interest here. We picked, our computer failed. We know we have a defective chip. What's the probability that it's Intel's fault? Now, the intuition there might be, well, it should be pretty low because Intel's chips are pretty good. Only 1% of them have problems. But what might seem surprising is that it turns out that it will be pretty high. The formula here, we want the probability of Intel given that it's defective, which is the probability that we get a chip from Intel that is defective, and then we divide that by all the different ways that we can get defective chips. That's the secret to this. The denominator is all the possible defects. The numerator is the defective one we're interested in. If I flip back to my little tree here, this is the case I'm interested in, but it's out of all of the defective cases. Which we'd already calculated. So let's get this non-defective out of here. What's the probability of this one happening? Given that we know that we're in the group of defects. So it's this one out of the total of these three. And that's what the formula is. It's the one you're interested out of the total number. We want the probability of, we want the probability of Intel given that it is a defective chip. So if you're really into the subscripts and symbols, well, basically Intel was group 1, B meant defective. So we want the probability of A1 times B given A1 divided by all the different ways that I could be defective, which is what we had calculated before. It was the 0.0125 was already calculated. It ends up being 68%, which is rather high. Even though only 1% of Intel's chips are defective, there's a 68% chance that it's Intel's fault when you find a defective chip. The reason for that being they have 85% of the market share. Even though their product is better than the others, it's still most likely to be their fault. And that's a number that might be hard to kind of predict as well. Your intuition might fail you a little bit on those until you get used to doing a few of these. I think that's enough for Unit 2. In the next unit, we'll move on to discrete probability distributions. But that's enough for today. I hope you all have a good one.